Hello, this is video 26, and as you can see, I thought I would get a little head start, and I kind of got carried away. I didn't want to have to make you sit through me writing all this code on the board, so I was going to write a couple of lines, and once I got going, I couldn't stop myself. But we're still looking at the put function, getting closer and closer to perhaps an actual implementation. The public wrapper is one line. Here's a public wrapper. The put, when the main program or whoever is using this dictionary implemented as a binary search tree, when they call put, they're going to pass in a value type item. That's the cow and the picture of the cow and the history of the cow and all that other stuff. In other words, that's the whole package. That's what they want to put in the dictionary. And I've called that new item. That's hard to read, but the parameter here is new item. I don't know if that matches the prompt or not. I forgot to look. But anyway, whatever it is. And here we go. It turns around and does nothing but calls the recursive overload of put, except the recursive overload needs more than just the new item. It needs the root of the whole tree, which I very cleverly titled whole tree root, which in my particular case, let's see, what would that be? The whole tree root would be the only private variable, and it would be initialized to 0 in the constructor. So in the very first case, we're passing in whole tree root, the variable, which has a 0 in it, and we're passing in the very first item, which I think was pig, to be inserted in the binary search tree. All that is set up. Now, you might wonder, what's the return doing out here? Well, remember, put could be successful or unsuccessful in the general case. We don't know if the item is already there or one that has a matching key. So what we've got to do is, every time we call put recursively, put, we sit there and wait, and whatever they send us back as a return value, just chain reaction, we turn around and return that to whoever called us. We've seen that before. You had to do something like that in your haystack program. But the recursive, we can't ignore the recursive return values from the recursive overload because they're telling us whether or not we eventually inserted this new data item at the bottom of the tree, this new value type item called new item at the bottom of the tree. Here, I got started with, and I wasn't going to do this, but yet I did it anyway, for one specific reason. Can you guess what it is before I open another colored marker? Well, it's going to be private. It's got to be in the private section. It's an overload. It's got the same name. It's still a member function. We're still passing in new item exactly the way we did before. Constant. It's a constant reference. And here, constant reference is not really, it is true that we don't want to change it. Yes, we don't want to change it. That's why we put const out front. But it could be that that picture of the cow and all that stuff, that could be huge. And if we pass in a gigantic value type item as a value parameter, then the system has to copy that whole thing into that local parameter variable, which could take time, it could take up a lot of space, and we don't do that. So instead, we just pass in the address. So these two, it's almost like they cancel each other out. We pass in by reference to save space. All we're doing is passing the address of the item, because we might not even have to copy it into the tree anyway if it's already there. So we save space by passing in nothing but, in effect, a pointer value. And it's constant so that we can't change the new item. We can't change the picture of the cow. Okay? All of that is to describe that. Here's the weird one. Here's why the pink. I don't think we've seen the likes of an ugly data type for a parameter like that before. Two operators, two different symbols in a row as part of the data type. What could this mean? Well, the root of the whole tree, that is a pointer to a node. It's a node pointer. But if you really absorbed everything that was in video 25, then you realize, oh, you know what? We might have to change the value of the root parameter that's passed in. If they pass us in a root parameter that has value 0, we need to replace that and make that replacement value stick. So we need to either pass in perhaps the address of a left child to somebody, or a right child of some node, or maybe the root of the whole tree, but we have to have the power to change it. So this, ladies and gentlemen, the root parameter has data type reference to a node pointer. The actual data type is node pointer. We're passing in a reference to that thing, a reference to a node pointer so that we can change the node pointer. When you say it out loud, maybe it makes more sense. When you see it in writing, node star ampersand, it just looks ridiculous. So that's why I decided to go ahead and do that line. And what I want us to do is iterate again. We're doing iteration after iteration of inserting that cow and pig and dog and everything. This time, let's get serious about it, or maybe a little more serious. What I want to do is, with your able assistance, you can yell at the screen and I'll hear you. Let's see if we can transform what I was talking about in very abstract terms about go to the left, go to the right, and all that. Let's see if we can turn that into pseudocode steps. Now, if you are developing your own, based on earlier videos, if you're developing your own pseudocode steps for the put algorithm, you might want to just stop this video right here, cut, and then come back and look at it starting at about 5 minutes and 40 seconds. Come back and look at it later, because this might give away all your fun. However, don't worry, you'll still have fun. I am not going to go through the get operation. I'm not going to go through print debug. I'm not going to go through any of the rest of it. In other words, for most of this program, you're going to be more on your own than you've ever been. What I am going to do, though, is have more times available for Zoom to talk about this with you individually if you want to, maybe even a regularly scheduled class period. So focus on this really hard so that you can ask questions about the other functions if you need to. This is, what do I even call this? Toward a put algorithm. I don't know that that's the best title, but that's the title I'm going with. And the algorithm, we'll start here, the recursive put. So very abstractly, like I did the traversals, I'm going to say we've got a thing called put, and we're passing in this thing called root, and I'm passing in a value that I'll call, do I want to just call it value? I don't know. Yeah, I'll call it value. I'm going to regret that. I'm almost certain, because I'm going to use the word value and use it. I'm going to call it new value. I just got to do something. I'm sorry. New value. Okay. And away we go. Now, this is, since this is the toward a put algorithm with the point of view of the private overload, this one's already done. We don't have to do anything else with that. We do need to take care of any base cases. Base cases, and I'll go ahead and make it plural. I'll stop saying it's one base case divided into several pieces. It's perhaps more intuitive this way. When do we bottom out? When do we stop? Now remember, we forget about all this. We can't see that entire Christmas tree up there with all the ornaments and all the branches and everything. All we know is somebody passed us a reference to a node pointer, the weirdest data type ever. Somebody passed us that, and they're calling it root, and they passed a new value they want to insert in the tree. Okay? What if they pass in a 0 pointer? As we know, that's the external node. Here's the base case. If root, I'll underline the variables so they stand out. If root is external, or I'll put it parenthetically over here. In other words, i.e. equals 0. If root is 0, what do we do? Okay, now you yell at your screen and tell me what we do. You are exactly right. We need to set root to the address of a new node. In other words, we call new, dynamically allocate it. Set root to the address of a new node. Now that we've got something that we point at, we need to do some more sets. Set root data, root arrow data, whatever that field is called, I don't know, to new value. And anything else? Oh yeah, set root left and root right. I won't write those as there. You can put it, yeah, I'll put it in there. Set root arrow left and root arrow right. Now, if I were a very responsible professor, I would say set root arrow right and root arrow left to be the addresses of external nodes. I don't have room to write that over there. So I'm going to say that to zeros. We know what that means. That's what we did. We set the external nodes to zeros to represent external nodes. Okay? If it's not external, oh, now wait a second. What did we just do? We just now hung a new node off the tree somewhere. Maybe a new left, maybe a new right, maybe a new root. I don't know. I don't care. But I need to return success. Return true. Also known as success. And I'm out of here. Now, I could say else, except as we all know, the special case of the ifs and the elses and so forth in functions are, if there's a return statement in the true part, in the if part, then you don't really need an else. It's an implicit else, because if we're still here, that means this condition was false. Otherwise, we're gone. We've already gone back to the main program by now. What if we're still here, the root was not external? Well, there's a possibility. There's still no work to do. If root, arrow, what am I calling it? Data. And this is pseudocode, so I'm not going to write an equal sign. I'm going to do equals, EQs. If root arrow data equals new value. Then set root to the address of another new node. Set data. No, you know better than that. If they're equal, there's no work to do. We get out of here. We're unsuccessful. Return false. You know what? There's almost no chance I can write the rest of this algorithm down there. I will put an observation down here. I think that's all the base cases we have, isn't it? If it's not, then I'll go back and have to patch that up later. But I think this is it. If the root is external, it's 0. Freeze. That's what I was doing in the earlier videos. Freeze. Replace the 0 with a pointer to the new node. Initializes children to external nodes left and right to 0 and return true, and we're done. If root data equals a new value, return false. If we're still here, and I'll put that as a comment, and then I'll have to wrap around to the top of the board. We'll see how well that works. If we're still here, then what do we know? Then either or, and it has to be one of these two, either the new item is less than the root's data value or it's greater. Then, how am I going to write that succinctly? New item must be either less than or greater than root arrow data. Put your logic caps on. Covers all the possibilities. Either there's nothing there at all. There is no root node. In which case we're gone. We put a new node in. Now there's a new root node, but we're done. So return true. What if the root... Now notice, now normally, did I say this before? It doesn't really matter what order you test the base cases. Actually, it does. In this case, it does. Look at our base cases. If root's 0, put in a new node and return true. What if I tried to test this one first? If root arrow data equals new value, what if root is 0? Crash, burn, segmentation fault, core dump, all those bad things. So in this particular case, yes, it does indeed make a difference which one of these we test first. We got to make sure there actually is a root pointer before we start trying to dereference it to get the data value. Now that I've said that 5 or 6 times, let us continue. If we're still here, then the new item must be either less than or greater than the root data. Maybe that's painfully obvious, maybe it's not clear, but that's the only option left. If it's not equal to it and we've returned false already, then it's got to be less than or greater than. What does that mean? What are the philosophical implications of that? That means that we're either going to move to the left or move to the right as we go down the tree. And rather than erase this and do the wraparound, you know what? I'm going to do a separate video of nothing but the inductive cases. So I'll see you online.